Video Lecture 4.2, Atmospheric Lifting Mechanisms, which is just a fancy way to say, how do you make it rain? And we're going to do this all without even having to get out any single dollar bills. Key to understanding how to make it rain is all we have to do is get warm, moist air to rise. And so we can get warm, moist air to rise. We know eventually it's going to condense as it cools, as it goes to a higher elevation, and eventually fall back down as rain. So that's the key. How can we get warm, moist air to rise? So let's focus in on the 4 different ways in which we can make it rain. So let's start off with one that we've already discussed this semester, and that's convergence. We find that along the equatorial low pressure trough, also known as the intertropical convergence zone / ITCZ. Here's our good friend, the Hadley Cell. And so we got the trade winds from the northeast and the southeast come together, and those trade winds come together there at or near the equator, forming that dense rain band that we discussed in a previous video lecture. And so then the low pressure forms. Situation is warm, moist air condenses as it cools, and eventually falls back down as rain. So the Hadley Cell, we've already discussed this, and so this would be our first example of an atmospheric lifting mechanism, simply convergence, which can be seen here in this image that shows that horizontal line coming from northern South America all the way out towards the Pacific to the left side of this image here. You can see that dense rain band illustrating convergence. Next up is convection. Key to understanding convection is you have to have moisture on the surface. And so what ends up happening here is moisture on the surface is heated by maybe an intense sun period during the day. And so what ends up happening is that warm, moist air rises, just like a hot air balloon. So that moisture, that warm, moist air, then rises, eventually condenses, cools, and falls back down as rain. These are often referred to as popcorn clouds. Popcorn clouds because they look like popcorn, but also popcorn clouds because they essentially pop out of nowhere. So oftentimes weather forecasters have trouble predicting these because, once again, they pop out of nowhere. One of the other characteristics of convection clouds is they are always in the summer hemisphere. So when we think about convection clouds, we're not going to see them in Indiana in December, January, and February. We're going to see them in our summertime. Some examples, there's that daily afternoon shower that happens in Florida. So that's an example of convection. We'll be able to see this in video lecture 4.6. We'll also be able to see convection clouds in Mexico in video lecture 4.6. Also, Nebraska oftentimes has severe weather in the afternoon, and so this is another example of convection. Others would be the Smoky Mountains. The Smoky Mountains, obviously, they have the name Smoky, but it's not because there's burning and smoking and all of that, no cigarettes. It's the Smoky because it kind of looks like it because there's always the haze. And so once again, we have to have moist surfaces. So afternoon showers that happen often in the Smokies because we get that moisture at the surface is heated, then eventually cools and falls back down as rain. Also rainforest. We're going to see several examples of this here in future images. So the popcorn clouds over rainforests help to fuel a lot of that vegetation that requires so much precipitation that we find there. Also in Indiana. Indiana, like I said beforehand, when we talk about stratocumulus clouds, we have oftentimes the afternoon, and so we have moisture on our surface. It's been heated up all day long, and so eventually these stratocumulus clouds start to line up throughout the afternoon here in Indiana. Here's Florida, of course, and we can see in this image, we can see a lot of blue there in central Florida, and that blue obviously is water. And so there would be a great example of showcasing the fact there's a lot of surface water. Of course, at the southern tip of Florida, there's the Everglades, which is a swamp. And so throughout Florida, there's sinkholes and lakes and swamps, and so a lot of surface water. Before I go further, let me build on something we've talked about beforehand. So during the day, at the beach, in the morning it's kind of calm, but then throughout the day, an ocean breeze forms. So that's just simply because of that low pressure that develops over land, like I've talked about beforehand. So we get this typical wind pattern during the day. So with that idea in mind, we can go back to Florida here, where we have a lot of surface water, and we got the Gulf of Mexico on the left-hand side, the Atlantic Ocean on the right-hand side. And so what ends up happening is the surface is superheated throughout the afternoon. And so what ends up happening is we get the process of evaporation and eventually condensation. So what helps to give that cloud, or what helps to get that warm, moist air to rise is what I talked about in the previous slide. So those ocean breezes coming in help to lift keep in mind those are cooler ocean breezes, then the surface help to lift this warm, moist air mass. So that's very important to understanding this process. And so eventually it gets to the point where condensation becomes precipitation and falls back down as rain. So essentially one of the things we think about the surface of Florida is constantly rejuvenated by this same process. And so the moisture that falls during this daily afternoon thunderstorm is essentially the same moisture that the next day is going to be superheated. And so it kind of causes this cycle of daily afternoon thunderstorms like I've mentioned, which we can really see here in Florida. And so this is an image that shows water vapor over Florida. And you can see the convection clouds pretty much all over the entire state, except for one part, and that's Lake Okeechobee. And so I ask you why. Our third atmospheric lifting mechanism is orographic. The idea here is you have warm, moist air that's moving, and so all of a sudden it's moving along, it's kind of cruising, then boom, something is put in its way. And so it's going to force that warm, moist air up. And so you can have any type of upland or mountain, you're going to have oftentimes orographic precipitation that dominates that area. What happens here is you have a wet side and a dry side of a mountain or an upland. So the wet side often referred to as the windward side, whereas the dry side referred to as the leeward side. So that the dry side creates a situation of what they call the rain shadow effect. And so the situation where on one side it's quite dry, which we'll see clear evidence of on the following images. Here we'll describe orographic precipitation as a warm, moist air mass is going to be forced upward by this mountain. So this pocket of warm, moist air is going to be moving because that's the direction of the wind. Would say the westerlies are dominating that wind pattern, for example. And so eventually that warm, moist air, because the mountain's there, because topography is there, is then going to condense, cool, and fall back down as rain. So the effect then is you're going to get an area that's quite lush on one side of the mountain. Eventually this pocket of air will reach the top of a mountain or top of an upland surface and then eventually continue on the other side. The wind pattern continues to move that pocket of air. Eventually that pocket of air will move along, and essentially the simplest way I can describe it is it spews out all of its fluids. So it spews out all of its fluids on the one side, but then as it descends on the other side, it becomes quite dry, resulting in a rain shadow effect on the leeward side of a mountain. Here's an isoline map that shows precipitation. So areas with the highest precipitation are in blue and purple, and places with the least amount of precipitation are red, yellow, and orange. And what you notice is there's definitely a clear pattern here of precipitation along the Pacific coast, whereas further inland it's quite dry. And key to understanding that is the fact that right through here is what they call the Cascade Range, a mountain range. And so this mountain range creates a situation where it's wet on one side and quite dry on the other. So we're going to look at two places that are on opposite sides, the first being Seattle, Washington, the other one being Walla Walla, Washington. Here's an image from Seattle, and Seattle is known for their all-day kind of drizzly rain situation. When we think about why coffee is so popular here, because they're not growing the coffee there. It's popular because it's pretty much all day long dreary, and coffee helps to keep you awake at 3 o'clock in the afternoon when it looks just like it did at 9 a.m. Another thing, we think about grunge music, kind of depressing music from the 1990s, where it was kind of like a lot of My Life Sucks and all of that. Grunge music came out of Seattle during the 1990s, and if you think about the situation, the characteristic weather here, it makes a lot of sense. And Seattle's known for its dense pine and evergreen forests, which we find here. And so the forests, once again, are fueled by a good amount of precipitation that occurs on the windward side of the Cascades. However, on the opposite side of the state, it looks completely different. And so, of course, this is a field in which it's been altered by humans, but nonetheless, it gives you an indication clearly of the amount of precipitation that falls here in Walla Walla, Washington. And we'll do a quick pop quiz. Where can you see orographic precipitation in action? So think about where you can see upland areas and their influence on precipitation levels. Let's go ahead and pause it. And then right now, you can now see the results.